This is the Section 2.2 Mathcast. It contains 5 lessons. Again, the teacher notes are extensive in these lessons, and watching the Mathcast should not substitute for reading the teacher notes in each section. Now that the students know how to obtain a least squares regression line of best fit, they can begin to describe the association between two quantitative variables with more specific statistics. They derive and calculate the coefficients of correlation and determination and interpret these quantities in the context of statistical situations. Students will calculate and graph residual plots to assess the fit of linear models to data. Students will also preview the concept that statistical association of two variables does not show cause and effect by doing a lesson which is a preview of material extended in Chapter 4. The standard deviation of the residuals from Section 2.1 has a useful meaning on its own, but it's not a good way to compare the strength of association among different data sets because of its unit dependence. However, by standardizing all of the data points, the units are eliminated, but the shape of the scatter plot remains unchanged. This provides the basis for the formula for the coefficient of correlation, R. Students explore its characteristics, such as the sign of R indicates the direction of the relationship. Because points in the first and third quadrants contribute positive products to the sum, while points in the second and fourth quadrants contribute negative products to the sum. And that the magnitude of R between 0 and 1 indicates the strength of a linear relationship. Lesson 2.2.1 includes a review of z-scores and a comparison of scatter plots made from standardized points versus their originals. The students discover that they are the same. Students are asked to calculate R by hand just once, and they see that R is the slope of the standardized line. There is a Desmos e-tool available for problem 246 that explores the magnitude of R and its meaning. If you don't have access to the e-tool, use the further guidance provided in problem 2-47. There is a math notes box that demonstrates a common type of computer output used on the AP exam and throughout the course. In Lesson 2.2.2, students use algebra to investigate more properties of R, including the fact that it's unchanged by switching units or even switching explanatory and response variables. Algebra is also used to show that R is indeed the slope of the standardized LSRL, and that the LSRL can be found from a few statistics, such as means and standard deviations of x and y, and the coefficient of correlation, rather than having to use all of the data. This fact is often used on the AP exam. Students have the opportunity to prove that there is an algebraic solution to the LSRL that will minimize the sum of the squares of the residuals, showing why and how our computers and calculators can come up with this extraordinary solution without having to guess and check. The algebra in problems 256 and 258 is rigorous, and you should personally review it before the lesson so as to increase your confidence in the processes. If you're teaching this material as an introductory statistics class, you may want to substitute an in-class discussion for the concepts presented here. For AP students, challenge them to persevere and tell them you expect them to struggle. Use your judgment as to how productive their efforts are before providing scaffolding. Avoid the temptation to resort to robotic memorization of facts about the coefficient of correlation, and leave some room for aha moments later in the chapter. The math notes for R and R square are found in Lesson 2.1.5. An extension of problem 258 is a proof for the fact that R squared represents the percent improvement in predicting a response variable one can expect using an LSRL instead of using the response variable mean. This is discussed in the mathematical background section of the teacher notes and again in lesson 215 where the coefficient of determination is introduced. Demonstrating, deriving, and discovery of the characteristics of R is more difficult than rote memorization of facts. This lesson is challenging, but holds true to the general CPM philosophy of emphasizing meaning over memorization. Lesson 223 begins with a demonstration of strong outliers and their effect on the LSRL, followed by a situation that reviews LSRL concepts thus far. Students then create and interpret residual plots, gaining experience in determining what a pattern looks like and what it means to the relationship. Lesson 223 requires students to make a number of scatter and residual plots using your chosen technology. You should prepare in advance so you can demonstrate these processes smoothly. The Bivariate Data Explorer and Grapher E tool provided creates residual plots automatically and will speed up this process considerably over using calculators. It takes scatter plots, the standard deviation of the residuals, the coefficient of correlation, and residual plots all working together in order to evaluate a model. This is from problem 267, where the dry ice is evaporating over time. As we can see in the scatter plot, it looks like a linear model fits well. We also see that the standard deviation of the residuals is quite low in this context, while the coefficient of correlation is quite high, at least in a negative sense. This appears to be a well-working linear model. Now we add the residual plot and we discover that there is definitely a pattern in the residuals. Does that mean that the model is no longer useful or valid? Not at all. What it means is that there is probably a curved model out there that would fit the data better, but it doesn't mean that our linear model is necessarily useless. Here is the residual plot from a different data set. It has exactly what we would like to see in a residual plot. That is, no discernible pattern around the regression line. Is this validation of a useful linear model? Not at all. We need to examine the scatter plot and other statistics first. The scatter plot also shows a random pattern of data, and so a linear model is not necessarily a fit at all. Our standard deviation of residuals is high, and our coefficient of correlation is extremely low in magnitude. So even though our residual plot looked good, our other statistics and scatter plot show this to be not a useful model at all. Lesson 224 opens with a problem that reviews residual plot concepts and then transitions to a situation where the association between variables is very intuitive, but the suggested causal relationship is absurd. Students are introduced to the term confounding variable and are given some examples of how they can be associated with the explanatory and response variables, but still remain a hidden cause. In problem 278, don't let the students dissolve into arguments about the truth of the associations. You may assume that the associations given are true. It's the confounding causes they need to search for. Consider this actual news headline found in problem 278, where students are to assume the associations are true, but determine at least one possible confounding variable that could be the actual cause. In this situation, cancer rates are the response variable. students will likely be able to come up with variables that affect cancer rates, such as sun exposure or toxic chemical exposures. However, these are not tied to our explanatory variable, which is calcium in the diet. So a confounding variable would be tied to both calcium in the diet and cancer rates. Consider a variable like youth. Perhaps young people drink more milk than older people, and so they have more calcium in their diet. And also, young people have lower cancer rates than older people. So maybe calcium in the diet is just an indicator of being young, and being young is what keeps your cancer rate low. Or maybe people that consciously eat calcium in their diet have a healthier diet overall that might include more things like green leafy vegetables. And perhaps it's the green leafy vegetables that are lowering the cancer rates, not necessarily the calcium. Because youth and eating green veggies are both tied to cancer rates and calcium in the diet, they are good examples of confounding variables. Lesson 224 also serves as a preview for Chapter 4 concepts, where an understanding of confounding variables is critical in recognizing the need for well-designed experiments over observational studies in order to determine cause. Lesson 225 begins with students exploring what a percent improvement represents. First, for two predicted values compared to an actual value. Then for two entire linear models, one always predicting the mean of the response variable versus the other using the LSRL. Students compare the percent improvement in predictions using the LSRL over using just the mean of the response variable to the value of R squared, and they see that they are the same. This language is then formalized in a math notes box. You will want to prepare by reviewing problems 284 and 85 to make sure you're comfortable guiding the students through finding a process that finds the percent improvement so you can keep the class moving. You don't want to spend an entire class period on these two problems. The fact that R squared has such a specific and useful meaning, and that it can be found by literally squaring R, seems a bit magical, like dividing by n-1 fixes the bias and sample variance. The proof of this is an extension of problem 258. While correlation and regression are important AP topics, they are somewhat standalone in the course. They are revisited again in Chapter 12 when the LSRL components of slope and y-intercept are considered sample statistics from a larger sample distribution, necessitating inference techniques.